Hey, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So I also took my Bachelor's of Science at this institution as well in pharmaceutical chemistry. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or tutoring, then check out the links in the description below. So now I'm just going to get started on the first set of questions for today. Okay, so question number 1. Question number 1. Write a formula for the compound that forms between calcium and each polyatomic ion. And then they give different options like hydroxide, chromate, phosphate, and cyanide. So first, let's just find out the charge that calcium has as an ion. So the calcium ion has a +2 charge. So I'm just going to write 2 plus charge. So let's look at the different polyatomic ions it will form. So for calcium 2 plus hydroxide, hydroxide ion has a -1 charge. So therefore we need 2 hydroxides for a compound. So therefore the first answer is calcium hydroxide, and there's gonna be a 2 there to show that we need 2 hydroxide ions for every 1 calcium ion. So next, let's do calcium plus chromate. So the formula for chromate is C chromium O4, and then its ion has a 2- charge. So it'll just form at like a 1-to-1 ratio to get calcium chromate. And then for C, calcium plus a phosphate. So the formula for phosphate is PO4 3-, so it has a -3 charge. So therefore its compound shows that we need 3 calcium atoms, and we also need 2 phosphate ions. So to do this, I kind of just cross multiplied. So since phosphorus has a -3 charge, calcium has 2, I just kind of cross multiplied it to get those values. And then for D, let's do calcium. And the formula for cyanide is just Cn-, so it just has a single -1 charge, so we need 2 of those ions to get calcium Cn2. So let's look at the answer from our junior tutor. It looks very long. The formula of the compounds formed between calcium and the given polyatomic ion. It doesn't look like they actually wrote down the answer. They just have the rules, which is like, this is all correct, but they don't actually write down any of the answers. It's kind of looks like a fill in the blank kind of thing. Okay, so they have a lot of the background done, and they talk about like the different charges and what the subscript should be. I'm just gonna say explanation is correct, but actual compounds are as follows. The question asked to write a formula for the compound, but this person just kind of explained how to do it. So even though the explanation is correct, they didn't really answer the question. So I'm just going to say that the explanation is correct, but the actual formula for the compounds are as follows. And then I just gave the answers. So that solution was incorrect. Okay, so question number 2. Draw the major monobromination product when the following alkane is subjected to radical bromination at 25 degrees Celsius. If there is more than one product, both may be drawn in the same box. So before I answer, I'm just going to write what the stability of the alkyl free radicals are, because that will help us answer our question. So basically the stability of alkyl radicals, it depends on how many carbons are attached to the carbon that contains the radical. So basically they follow the order. When you have a 3-degree carbon, it's going to be the most stable. So it's when the carbon that has the radical is attached to 3 other carbons. So 3 is greater than 2 degrees, which is greater than 1 degree. So let's look at part A. You'll notice that it is this alkane. Say it reacts with one equivalent of Br2 with light. So I'm just going to draw down the same alkane pretty much, and we're going to try and figure out where the bromine is. And you'll notice that this carbon right here is a 3-degree carbon. So that means that when we do this mechanism and it needs to have a radical as the intermediate, the most stable radical is going to form at this tertiary carbon. So therefore, our final answer will have bromine on that carbon as well. So we can do the same thing for part B. So this time we just have like a linear alkane. And basically, since this compound is symmetrical, it's just going to brominate at one of the carbons that is the 2-degree one. So we know it's not going to form at the end because since that's a 1-degree radical in the mechanism, it's not likely that the bromine is going to form there. So basically I just drew a bromine coming out of there. And this, to name them, the first one is 3-bromo, 3-methyl pentane, since there are 5 carbons in the parent chain. And then the major product for this one is 2-bromo butane. Okay, so let's check out the answer from our junior tutor. They drew out all the different possible products that you could get, but then they circled which one is the major product. So here they got it right, where it will form on the tertiary carbon. And over here they did the same thing. It's going to form on the secondary carbon. So this solution is correct. Okay, so this solution is correct, and we can move on to question number 3. Consider the reaction between butyllithium and ethanol. Label each reactant in this reaction as a, I'm assuming like a Bronsted acid or a Bronsted base. So let me write down this acid base reaction. We have butyllithium, which has the following chemical formula: C4H9 lithium plus ethanol. Okay, so now let's identify which one is our acid and which one is our base. So our acid is the proton donor. So let's look at both options and we'll see that our ethanol acts as the proton donor. So acid, and then our base is the proton acceptor. So in this case, it's the butyllithium. Okay, so I'll just also write out the mechanism that takes place. So we have a slightly negative carbon attached with like a slightly positive lithium. So the carbon is actually going to deprotonate the ethanol and bring the negative charge onto the oxygen to give our final products. And then this negatively charged oxygen will be stabilized with the positively charged lithium. Okay, so let's look at the answer from our junior tutor. Butyl lithium accepts H plus ions, hence it is a Bronsted base. Ethanol releases H plus, hence it's a Bronsted acid, and then they have the same mechanism that carries out. So this solution is correct. Okay, so let's move on to question number 4. Construct a simulated HNMR spectrum for methyl propanoate. By dragging and dropping the appropriate splitting patterns into the box, it will shift baseline. And by dragging integration values into the small box above each signal, items may be used more than once, and the peak heights do not represent integration. Okay, so this is an HNMR question. So let me write out the structure of the methyl propanoate. And when you want to answer HNMR questions and you're given like a structure, I like to first identify what kind of hydrogens are on, what kind of hydrogens are present. So let me actually write this out as like a CH2. And then if you look at each of the different hydrogens, we want to look at all of the chemically non-equivalent protons, because that's how many signals we will have. So let me write that down. The number of signals that we see is equal to the number of chemically non-equivalent hydrogens. So basically, let's look at all the different hydrogens that we have in methyl propanoate. We have like a methyl group here. And those hydrogens are in a different chemical environment than these hydrogens, because this is on a carbon that's attached to a carbon that's double bonded with an oxygen. And similarly, the hydrogens on this methyl will be different as well, because it is attached to just a single oxygen. So let me label these hydrogens as A, B, C. And now we're going to first talk about like splitting patterns. So when you have splitting, we're going to do the n+1 rule, where n is like your number of neighbors. So this all makes sense once I start actually writing it down. in terms of shifting, depending on where they are, like what their environment is, they'll all have a different shift. So let's look at A. We have just like your normal, like carbon attached to like a hydrogen. Nothing else is like affecting it. If you were to look this up at like a HNMR shifting table, you'll see that this signal usually occurs at around like 1.2 ppm. So we can do the same for the hydrogens in B. So we can write it out as like where there's a double bonded carbon, and it's going to be the hydrogens here. They typically have shift of 2.4 ppm. And then lastly, for C, it's basically the hydrogens on the other end of like an ether group. And they typically have a shift of like 3.5 ppm. So these are values that you would just be given in like a table. So let me draw out just like a rough HNMR spectra. Give myself some space. And I'm going to start at like the 4 because that's just where everything takes place. This is ppm. And now I'm just going to be looking at how each of these hydrogens should split. So let's start with A. If you look at its neighbors, there are 2 hydrogens. So if we do the n+1 rule, then this should split as a triplet. So it's 2 plus 1. And then let's look at the hydrogens in B. Its neighbors, it has 3 hydrogens. So n+1, it'll split as a quartet. And then for the last one, there are no hydrogens on this oxygen. So 0 plus 1, it'll split as a singlet. And then now that I know its splitting patterns, I can put it on the spectrum. So the one that splits as a singlet, I'll draw here. Oh wait, I said 3.5-ish. That was not a straight line. And its integration value will be 3H, so that's just how many hydrogens are with that peak. And then let's look at the one that splits as a quartet. It is at around 2.4 ppm. I'm just going to draw it splitting like this. And there's only 2 hydrogens, so its integration value is 2H. And then lastly, for the hydrogens in A, it'll split as a triplet at around like 1.2 ppm. I'm just gonna do like a triplet there. And its integration is 3H. So let's look at the answer from our junior tutor. They drew out all the different hydrogens that are present. They talked about the splitting and using the n+ rule. And then they have our singlet here. And then, yep, our 2H quartet around here. And then the 3H triplet there. So this solution is correct. So an H&MR spectra actually tells you a lot of things. Just take some practice to try and analyze the different spectrum. But they're really helpful when you don't know what your compound is. So let's move on to question number 5. Identify the correct values for a 2p sublevel. Identify, oh, it's just the same thing. And then they just give us different options. So let me just write down these options so that it's easier to read. For A, n equals 2, L equals 1. So I'm just going to write out all these values. Okay, so for a 2p sublevel, our n value corresponds to the number in front of it. So it is 2. And then for your L value, typically it's based on like the letter. So I'm going to write down all the different S, P, D, and F. So for S, its L value is 0. For P, it's 1. D is 2. F is 3. So for 2P, its L is equal to 1. And then to figure out all your different ML values, it's just based on the range of your L. So when L is equal to 1, its range is going to be -1, 0, and +1. So those are all the different values that you could have for a 2p sublevel. Let's just look at all the different options they give us. Off the bat, we can cross out C, D, and E because all of their n values aren't equal to 2. And then just looking at A and B, n equals 2, L equals 1, ML equals 0, or ML equals +2. So we know we can cross out B, and our correct answer is A. Let's look at the junior tutor's answer. So they wrote out how they would answer it. So the solution is correct. And then I'll just kind of point out option A. Where n equals 2, L is equal to 1, ML is equal to -1, 0, or +1. Okay, but solution was still correct. Okay, so question 6. What can be said about an exothermic reaction with a negative entropy change? So let's write out When you have an exothermic reaction, then we know that heat is released. And when heat is released and you have an exothermic reaction, then your delta G value will be negative. Okay, so since heat is released, that means our delta H will also be a negative value. Since heat is released. And in the question, they say that it's an exothermic reaction with a negative entropy change. So I'm just going to say that delta S is also less than 0 since it's a negative entropy. Okay, so let's look at the Gibbs equation, I believe is what it's called. Well, where it's delta G is equal to delta H minus T times delta S. If we want delta G to be negative, then that means that our negative delta H must be greater than the T, must be greater than the second part of the equation. So since we know delta S is going to be negative as well, it needs to be a low enough value that it doesn't give us a positive delta G, if that makes sense. So let me write down the explanation. So delta G will be negative only when the value of delta H is greater than the value of temperature times your entropy. And I'll just put in brackets when entropy is negative. Just so that we're on the same page. So therefore, if we look at all of the different options they give us, it's not going to be spontaneous at all temperatures, because at high temperatures, delta G won't be negative anymore. So it won't be spontaneous at all temperatures. It won't be spontaneous at high temperatures. It'll be spontaneous at low temperatures. So we know that that's correct. Reaction is spontaneous at low temperatures. Then different options, spontaneous in the reverse direction at all temperatures, so that's not true. Non-spontaneous in either direction at all temperatures, so that's not true as well. So here's the answer. They also got spontaneous at low temperatures. For the explanation, I'm assuming that these symbols just stand for delta. Delta G equals delta H minus T delta S. For spontaneous reaction, delta G is negative. Given that exothermic reaction with negative entropy change, delta H is negative, delta S is negative. So delta G is negative at low temperatures. Therefore, the given reaction is spontaneous at low temperatures. So this solution is correct. so let's move on to question number 7. Which acid in the following pair has the stronger conjugate base, NH4 or HF? So let me try to write out their dissociation of these acids. Okay, so I'll write down our 2 options and how they dissociate. So before answering this question, let's think about what they mean by like stronger conjugate base. So the strength of your conjugate base is inversely proportional to your acid strength. So I'm just going to write that it's proportional to 1 over acid strength. So the weaker acid you have, the stronger your conjugate base. So I'm just going to look at the pKa values of both of these acids. If you were to look up the pKa value of NH4, it's around like 9, I believe. But if we were to look at the pKa of HF, it's still like weak, but it's around like 3. So the smaller pKa value you have, the stronger acid you have. So HF has lower pKa. So it's the stronger acid. And the NH4 plus is the weaker acid. Therefore, it has the stronger conjugate base. So let's look at the answer from our junior tutor. It looks like they had a different question altogether. But the explanations all look right, but they don't really answer the question. I'm just going to say that HF has a lower pKa, which makes it a stronger acid. NH4 is a weaker acid. Therefore, it will have a stronger conjugate base. Okay, so that solution was incorrect. Now let's move on to question number 8. Given the structure that Give the structure that corresponds to the following molecular formula and H&MR spectrum. So it's another H&MR question, but this time they give us the molecular formula, and then they also give us kind of what spectrum would look like. So I'm going to do these in different colors so that it's easier to kind of see. So the first one is a triplet. It says T at around 1.93 ppm. So when you have a shift at 1.93 ppm, this corresponds to the hydrogens that are just like in the middle of two carbons. We have a singlet at 3.35 ppm. And this corresponds to like the hydrogens on the carbon that's beside an oxygen group. And lastly, there is another triplet at 4.49 ppm. And this corresponds to the hydrogen that is attached to a carbon, but that carbon is also attached to like another carbon. So how do I'll just do like kind of like that. So there's only one hydrogen involved on the carbon because that's attached to a second carbon, which is attached to an oxygen. And then they give us the relative integrals of all of these values. So I'm just going to do it in like a different column. And it's at a ratio of 1, 6, 1. But if we look at how many hydrogens that are actually in the structure, there should be 16. So I'm just going to multiply everything by 2. So it should be 2, 12, and 2. Just so that we can count out how many of the hydrogens are actually there when we draw our structure. So first, let's look at the singlet at 3.35. So since it's a singlet, then we know that it doesn't have any neighbors that have any hydrogens, and we also know that there are 12 of them. So basically, it's going to be at the end like that, and its only neighbor is the oxygen group. And then I'll draw out the CH that corresponds to the triplet at 4.49. So it should only have a neighbor that has 2 hydrogens. In order to split as a triplet, we're going to do the n+1 rule that I talked about earlier. but it's attached to another oxygen that has another CH3 group. So looking at this CH2, which is the triplet at 1.93, we can see that one of its neighbors has one carbon, but since it splits as a triplet, that means it needs to be bonded to two carbons, each with a single hydrogen, if that makes sense. So it has two hydrogen neighbors altogether, so it'll split as a triplet. And again, I'm going to just draw out the rest of the structure just so that we have the same number of hydrogens as the compound. And then I'm just going to color code where each of those hydrogens were. So the singlet hydrogens were here, so it's all of the hydrogens that don't have any like hydrogen neighbors. So this is the singlet. And then the triplet, there's only two hydrogens that have the triplet at 1.93. And then lastly, for the CH group, it's going to be these two here that also split as a triplet. Okay, let's look at the answer from our junior tutor. I'll use an asterisk next to the hydrogen for that resonance. So I get what they're getting at. Okay, so it's kind of like a confusing answer, but I'm guessing since the question already gives out the structure almost, I'm just gonna write down what I have. Yeah, so it's hard to write out what the structure should look like. But hopefully that will kind of answer the question. I'm still trying to understand what the junior tutor said. but I'm pretty sure it's correct if I were to actually try to answer this type of question. I just kind of helped out their answer a little bit. So the solution is correct. Okay, so now we are moving on to question number 9. What is the enthalpy for reaction 1 reversed? Where reaction 1 reversed is this carbon dioxide makes carbon monoxide plus, I don't think that's a 12, I think it's like a half of an O2. Makes more sense. So when you have the enthalpy of your reaction, this is equal to delta H formation of your products minus the delta H of formation of your reactants. So let me just specify for this question. The delta H of the reaction is going to equal to the delta H of formation of carbon monoxide plus let me look at, just want to make sure that it's all correct. Yeah, so it looks like they have a different question altogether for the answer. So I think we need to write down the reverse reaction of this. I think that's what it means by reaction 1 reversed. Let me label this as reaction 1. So reversed, it's going to be like the opposite. So if we look at it like that, our product is the CO2, and this time it's our reactants. So it's delta H is carbon monoxide plus half of the delta H of oxygen. So these enthalpy values are given in like a chart because they're just standard for those different compounds. So the value of the delta H of CO2 is negative 393.5 kilojoules per mole. For the delta H of carbon monoxide, its value is negative 110.5 kilojoules per mole. And then if you look at the delta H of an element such as oxygen, it's actually going to be 0. So that kind of just cancels itself out. And then we have the delta H of reaction going to be equal to negative 283.5 kilojoules per mole. So I think that the junior tutor might have gotten it from like a different question. Okay, but it also looks like they got this negative 283. So we know that that answer was correct. So let me just write out the answer just so that whoever's reading this in the future will just be on the same page. So okay, so I have the delta H of the reaction is equal to the delta H of the products minus the delta H of reactants. So let me just write out what I did. Okay, so I just wrote out what I did. I think we have time for one more question. So it says to draw the neutral organic products. So we have like a cyclohexane with a bromine reacting with H2O. So just some background about using water as like a reagent. It is actually a poor nucleophile. So not only does it proceed through an SN1 reaction, it also proceeds through an elimination reaction as well. So E1 mechanisms. So for our two products, we're going to get a substitution reaction where the bromine is substituted with an OH. And we're also going to get an elimination product where it forms this double bond instead of the bromine. Elimination. Okay, so that's our answer for that question. So that's why this person got it wrong, because they said the structure you drew is correct, but there is another major product. Think about which other mechanism is likely. And this junior tutor said the same thing. They have a substitution product and also an elimination product. So this solution is correct. Since water is a poor nucleophile. Okay, so that is all the time we have for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then please click the subscribe button and notification bell below. And if you wanted to submit a question of your own, then check out the links in the description. And also, if you liked today's video, go ahead and give it a thumbs up and a comment. And don't forget to share it with all your friends and classmates if they needed any help with chemistry. So this has been Donna from OneClass, and I hope to see you soon. Bye.